Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the variation of pressure with depth in a ideal fluid. So let us see that this is an ideal liquid which is at rest, and let us imagine a imaginary cylinder of radius of area A and of length dy, which is made up of this liquid only. So we are just imagining a cylinder which is made up of this liquid, which is a part of this liquid. Now the pressure at the top of this cylinder is P1 and the pressure at the bottom of this cylinder is P2, and the depth of this surface from the surface of the liquid is Y1, and the depth of this surface from the surface of liquid is Y2, and the height length of this cylinder is dy. So if we write down the mass of this cylinder, then its mass dm will be equal to rho into volume. Volume is a dy, and the mg, which is the weight of this cylinder, would be balanced by some upward force. Now you can see that this pressure is pushing this cylinder in the downward direction, while this pressure is pushing the cylinder in the upward direction. Now the cylinder is in equilibrium, which means that the net force due to pressure difference will be in upward direction and mg will be acting in the downward direction, and both will balance out each other. So the net force acting in the upward direction will be P2 minus P1 into area, and this will balance out mg. So P2 minus P1 is dp, and dp into area is equal to mg dmg, where dm will be equal to area A into dy and into g into rho. So cancelling out A with A, so dp will be equal to rho g dy. This is the pressure difference between the two surfaces of the cylinder. Now dp by dy will be equal to rho g, and this is plus rho g, which means that this is also called as pressure gradient. Pressure gradient. So as we go downward in the cylinder, the pressure per unit length will be changing, will be rho g. So pressure will be increasing in the downward direction. Now if we imagine a situation in which, let us suppose that there is this liquid and there is a point on the surface of the liquid, this point A, and obviously the pressure at this point A will be atmospheric pressure P atm, which is P naught, which is 1.015 into 10 raised to power 5 pascals, and pressure at B, which is at a depth of, let's suppose y, will be Pb will be greater than Pa, because we know that dp by dy is rho g, and dp is Pb minus Pa, and dy is y, and that is equal to rho g. So Pb minus Pa is equal to rho gy, and Pb is equal to Pa plus rho gy. So Pb will be equal to Pa is P naught plus rho gy. This is the pressure at the bottom point B. So at this level of B, at this point, let's suppose C, D, we can say that the pressure at B, pressure at C and pressure at D will be same, because they are at a same level from the free surface of the liquid. And when I say free surface, it means that I am referring to the surface which is in contact directly with air. So free surface is this one. So this is the formula. Now in the next video, I'll be bringing the case when the density of the liquid is variable. Thank you.